When it comes to 4.0 problems, at least regarding work and energy, all I'm looking for is that you demonstrate that you can use the work and energy concepts to find some kind of property of the object, be it the height or the velocity, and then use that in conjunction with some previously learned topics to show like a more comprehensive understanding of the physics topics to date. In this case, we're going to look at work and energy in conjunction with forces, which is the unit we just wrapped up. So this situation, again, there's a lot going on here, but I have a block that has a mass of 10 kilograms and it's flying down this ramp currently at 3 meters per second. It's 15 meters above the ground on an incline that's 38 degrees, and the coefficient of kinetic friction is 0.26. Once it reaches the bottom, it will slide along this frictionless section and slam into a spring that has a spring constant of 1,000 newtons per meter. The question is, how far will this spring compress as a result of all this motion and all this energy? All right, so it seems a bit complicated, but just like all our previous problems, we're going to set up our master equation. I know I have no work in because up here, it's moving because of its inertia. There's no force acting on it. There's no displacement that a force is acting on it. So there's no work in. But it has height and it has velocity, but there's no spring. So prior to reaching that spring, at the top of the ramp, it only has potential and kinetic. Afterwards, I've chosen my second point to be the spring. I could certainly choose here and go from A to B and then from B to C. I'm just going to say, hey, since the total amount of energy is always the same, I'm going to say this point is my start and this point is my end because I want to figure out the spring and how that's going to act, so that'll be my final point. So at the very end, I'm assuming that there is no EG because there's no height. It's hit this spring and compressed all the way so it's no longer moving, but there is energy stored in the spring. Now, the reason there's work out is even though I've chosen this point and this point, in order to go from point A to point B, it did have to ride over this friction. And while that occurred, work occurred. Friction took energy out of the system. It converted some of that into heat, into sound. And that is energy that, because it is no longer usable, will not wind up in this spring. Okay? So the energy lost during this phase will affect how far that spring compresses. So that's why I figured that at the end, whatever energy did not get dissipated is in the spring, and whatever did is the work out. So I start with height and speed, and I end with spring compression and some heat. Next thing you do, you just plug in your actual equations. MGH for gravitational potential, 1 half mv squared for kinetic, 1 half times the spring constant times the compression of the spring squared for a spring, and the work out would be force times the displacement times the cosine of the angle between those two variables. The next step would be to plug in everything we know. The mass is 10, it's on Earth, so the acceleration due to gravity is 9.81, and this happens to be 15 meters above the ground. In terms of the initial kinetic energy, the mass is still 10, but it's traveling at 3 meters per second. When I combine these, I find that the total energy of this object prior to any frictional forces, prior to compressing the spring, is about 1516.5 joules. That must be the total amount of energy anywhere in this problem. Now at the end, that 16.5 is split. Some of it is in the spring, and some of it has been lost due to heat, sound generation through work. Now the problem I have here is I know that the spring constant is 1,000. I don't know how much I've compressed the spring. I don't really know the force that's causing the work. I don't know over what distance it's causing that work, but I do know that since, in this case, I know it's friction, so the block is traveling down and friction's acting up. I know the angle has to be 180 because that's the angle between the direction of the motion and the direction of the force of friction. One important thing to point out, I know this is confusing. In physics, they tend to use a lot of the same variables. This is the displacement, but this is the displacement of the spring. So this has to do with how far the spring will be displaced. Whereas the work, since it wasn't performed on the spring, it was performed in the object, this has to do with the displacement of the object during the work that was occurring. So this variable, since it's associated with the elastic potential energy, is referring to how far the spring has been compressed. This delta x is still displacement, but it's the displacement of the object while the force was acting on it. So that would actually be this entire displacement here. What is this distance over which the friction was acting on that block? All right, so to find the displacement, because I think that's a little bit easier, you actually just have to go back and use some geometry and a little bit of like trig. So I have the 15 meters, which is given here. And I know that this angle is 38. So what I really have is a right triangle, and I have the opposite side because it's opposite the angle, and I also have the angle. If you're given those two, you can always find the third side, the other angles, etc. So since I have an angle and I have the opposite side, I'm interested in finding the hypotenuse because that is really the displacement of the object during the work phase. So if I want the opposite, if I want the hypotenuse and I have opposite, well, I have to think SOHCAHTOA. Which one of those has the opposite and hypotenuse? And that would be sine, SOH. Sine equals opposite over hypotenuse. So the sine of 38 equals the opposite side, which is 15, divided by the hypotenuse, which in this case is the delta x I'm looking for. Multiply both sides by delta x and divide by the sine of 38. So I wind up getting that displacement. That hypotenuse must equal 15 divided by the sine of 38. This total distance must be 24.4, which will go right here. Now all I have to do is find the force of friction, and I'll be able to solve for the compression of the spring. So to find that force, we have to go back to inclined planes. So here's my inclined plane. I draw my free body diagram, and over here I've just rotated it. So at this point, normal force is going up. I say up, I know it's at an angle, but I've rotated everything. My normal force goes up, friction goes backwards. Gravity's acting at this 38-degree angle. I could draw the net, I could draw the net x equation for my force, but since I don't actually know how fast this thing is going to be accelerating, it's not really going to be helpful. So I haven't included that just because it's a time waster. But I do realize that as it slides down the ramp, since it's not accelerating off the ramp or into the ramp, at least in the vertical direction, I know that AY equals 0. That allows me to set up my equation. I have the normal force acting up, gravity's acting down, and while I would normally use the sine of 38 to get that y component, remember for gravity on an inclined plane, and because it's measured off the y, the angle, I have to flip that. So in this case, I use the cosine only for gravity on an inclined plane. So my net y equation is the normal force acting up minus the force of gravity, which I've calculated here as 98.1, times the cosine of that angle. Because I know the acceleration of the y is 0, because it's not accelerating off or into the ramp, I know that normal force minus Fg, cosine 38, must equal 0. I can then solve that through and find that the normal force is 77.3. Once I have the normal force and I realize that I'm given the coefficient, I should see that those two things allow me to find friction. So the coefficient is 0.26. A normal force as calculated is 77.3, and the force of friction must therefore, when I multiply both sides by 77.3, be 20.1 newtons. The final solution is just going back up into here and plugging in the two values you didn't have before, your total displacement and your force of friction that's acting over that displacement. So I wind up, and just to show you, it is the same exact equation, 1516.5 equals 500 delta x squared. I take that, but I plug in my now known displacement over which the force acts. I plug in the force, which I make negative because it acts backwards, and this whole term actually comes to 490.44. Minus 490.44 from both sides, I wind up getting about 1026.06 joules equals the spring energy, 500 delta x squared, divide both sides by 500, take the square root, and you find that that spring must have compressed 1.43 meters. This is an awful lot of work here. I understand that. This is probably a little bit more difficult than the other 4.0. However, if you kind of realize as you go along, you could certainly start from this step, jump right to this step, realize you need force and displacement. You might not even have to draw this diagram out. You could probably just solve this by writing that one line, and so on and so forth. This one probably takes a little bit of time. I certainly understand that. But I do want to point out that while I've shown every step, I have seen this problem solved in as little as maybe 7 or 8 lines. So if you really know what you're doing, this problem is not necessarily going to take a tremendous amount of time. If you need the time to solve through everything, that's certainly understandable. Just realize how this problem was solved and why it's an example of combining what we've currently learned with previously learned concepts to show a deeper overall understanding of physics.